Okay. After you have installed the software, it doesn't appear on your desktop. So you go to your local drive, program file, and you see Petroleum Experts there. So you open the Petroleum Experts, that is it, IPM 11. You open this. There are about 6 softwares inside the Petroleum Experts. We have GAP, which we are going to use. We have ML, which we are going to use. We have Prosper, which is what we are going to use today. We have PVTP for PVT analysis. And then for R, we have Reveal, and then we have Resolve. These are the 6 softwares that we have inside the IPM. So what you do is, if you want the software to appear on your desktop, I will just right-click and I take Create Shortcut. Once you click on Create Shortcut, it's going to appear on your. They will tell you that you cannot create it here. Do you want it to be created on your desktop? You take yes, and then it will appear now on your desktop, like what we have here. So we are going to start the software. This is the interface. So we are going to double click here, and we have so many informations that we have to fill. Before we can start the software, before we can start any interpretation or whatsoever. The first thing we are seeing here is fluid. So you have to indicate the fluid type that you want to model. What type of fluid do we have in our reservoir? So we are going to either be having water and oil, dry and wet gas, or we have retrograde condensate. Now, when you have chosen the type of fluid, we are going to stay into oil and water. We leave it because we want to model the oil reservoir. And generally, when you are modeling oil reservoir, we know that water must always be present, no matter what. So the next step now is to go to method. What type of method do you want to use to model the fluid? There are 2 types of method. We have the black oil, and then we have equation of state. We have the black oil, and then we have equation of state. So I'll go to my PowerPoint. And from the PowerPoint, we can see the general PT diagram that is used to classify hydrocarbon fluids. We can see clearly from the diagram that we have at the beginning, at very low temperature and high pressure, we have our black oil. Generally, in the reservoir, the characteristics of oil is mostly controlled by pressure, while that of gas is mostly controlled by temperature. You realize that as you start from a low pressure, from a low temperature, I mean to say, as you're moving towards higher temperature, what is happening is the reservoir fluid is gradually changing into gas. So what we have here is our black oil. And then we move now to volatile oil, where the amount of gas content has increased. And then we have our critical point. We have our gas condensate. And then we may now have our wet and dry gas. Our wet and dry gas, the difference between wet and dry gas is that it will exist as gas only within the reservoir. But when you get to surface condition, you may see some liquids when it comes to wet gas. Some liquid will come out of the wet gas. But for a dry gas, you will not see any liquid. But both of them exist as gas within the reservoir. But at the surface, you may see some droplets of fluid when it comes to wet gas. So you realize that as you're moving in this direction, you're gradually moving from the oil domain to the gas domain. So at the early stage where we have only our black oil, the amount of gas in it is so small in such a way that it doesn't distort the behavior of oil that much. It doesn't distort the behavior of oil that much. But as you're moving towards the gas domain, the amount of gas increases. As a result of that, it now distorts the behavior of the oil. So in the black oil model, we are going to be assuming just three distinct entities. We have our oil, we have our gas, and then we have our water. These are the three entities that we are going to distinguish. Or basically, let's just say two, let's forget about water. So we have our oil and we have our gas. Our gas there, that's what we are going to identify in a black oil model. But as you're moving into the gas zone, where the amount of gas has increased or the gas oil ratio has increased, it is not sufficient enough for you to characterize each phase as discrete entities. So what will happen in that case is now they will now be given the composition of the various alkanes that are found inside that reservoir. They give you the composition of C1, C2, C3, C4, C5, and right to C whatsoever that exists. So we are having the composition of the various C chain that exists within that particular fluid. It's not like considering as entities, discrete entities like oil and gas again. No, you have to distinguish the various composition of the various C chains. So now here, what will happen is they are now using what they call the compositional model. We are going to use this concept again in Embark, so it's good we understand them. So what will happen now is they will now have to develop an equation of states that best define the condition of the liquid condition of that reservoir or the fluid characteristics of that reservoir. So we are going to bring out an equation of states. When we get to PVTP, which is one of the software that we have in this IPM, we are going to see how we can model equation of states using our PVTP. But for now, our interest is just to understand that we have the black oil model, then we have the compositional model that takes care of these guys, and then we have our black oil model that has a very gas oil ratio. So we'll go to our software. So for our method, we are going to take our black oil. All right. So the next step now is our separator. We have two types of separator. We have a single stage separator, and then we have two stage separator. So if I click, you see single phase separator, and then we have two phase separator. So what happens is a separator is a device at the surface that helps to separate the fluid at the end of the flow line. So when the fluid is flowing in the flow line, it gets into the separator. It now separates into its discrete phases. You have water going its way, we have oil going its way, and then we have gas going its way based on their gravity, because water will generally settle at the bottom. So there is a tube at the bottom that helps to drain the water. There's another tube that is connected at the central part that drains the oil. And then there's another tube connected at the top part that where the gas can easily flow. This gas is the lightest. But most of the time, since we are dealing with oil well, at that oil water contact, there may not be a good separation. So you may have another separator that is connected where oil, then you have another separation again the second time. So that's what we call a two-stage separator. But we are going to leave it easy. So we are going to just have our single stage separator. All right. So when we talk of emotions, I took time to explain the concept of skin. If you follow the free training we gave on the nodal analysis day 1, the concept of skin was explained, and one of the causes of that damage around the wear ball is what we call emotions. Emotions, where you have this interaction between things that are not compatible within the reservoir. So if you go to that lecture, you actually get a good picture of it. So our PVT warnings, we'll just leave it like disable warning, let's disable it. We don't want interactions and stuff like that. And then we have water viscosity. Of course, we need to know the viscosity of the various fluids so that we will know the ease at which they can easily flow. And then we know the properties at different PT conditions. So here we will just leave it as default correlations because you will definitely put in this value. Then for viscosity model, it's going to be either Newtonian fluid or the non-Newtonian fluid. So I'll go to my PowerPoint again. All right, this is what we have. So in our PowerPoint, we have a description of the Newtonian and the non-Newtonian fluid. So when we use these particular terms, we are simply describing the behavior of the viscosity with respect to shearing, with respect to shear stress that is applied on that particular fluid. If a shear stress is applied on that particular fluid, we know what shear stress is all about. We have two equal parallel forces acting in opposite direction. That's how shearing takes place. So when it comes to Newtonian fluid, you realize that no matter how you apply shear stress on the material, the viscosity does not change. That is the general behavior of our reservoir fluids, our oil, water, and gas. No matter how you apply stress on it, the viscosity does not change. Remember, we are not talking about temperature here. We are not talking about temperature here because generally when you apply temperature on any fluid, it will definitely, the viscosity will definitely change. So we are talking about applying shear stress at constant temperature. So for Newtonian fluid, the viscosity remains constant no matter the amount of stress you apply on it. But for a non-Newtonian fluid, you realize that the viscosity either decreases or it increases. Here we talk of shear thickening, and here we talk of shear thinning property. So generally in our reservoir, if we have a very heavy hydrocarbon, then we will now be, it sometimes behave like a Newtonian fluid. And it has this kind of shaping property. It has this kind of shaping property, but generally we are now talking about our normal, not very heavy, not a very heavy hydrocarbon. All right, software. So we are going to take our viscosity model as the Newtonian fluid. All right. We go now to our flow type. We have here the tubing flow, we have the annular flow, and then we have tubing plus annular. So we go back to our PowerPoint. All right. These are the various types of flow that we have. We may have a situation where the fluid is flowing only inside, because if you look at what is happening here, this is a tubingless completion where there is no tubing at all. We have only our casing and they are doing production. In this case, we have our tubing. This is our tubing. The well has been cased. The well has been cased. We have our tubing. They are doing production both in the annulus, the space between the tubing and the casing. So production is taking place simultaneously within the annulus and within the casing and within the tubing. In this other case, we have packers here. Yeah, that seals the space between the tubing and the casing. So we have the Packers comes in to block the annulus. We also have a device here that can block the tubing. So there are two ways in which production can take place here. Either they block this and then they open these Packers and the fluid flow within the annulus, or they block the tubing, or they block the Packers and then the fluid now is flowing through the tubing. So there are three ways in which the production can be taking place, either through the annulus, through the tubing, or both. So in this case, we'll just take our tubing flow, we'll just make it easy for the simulation to take place. So we are going to have our tubing flow. Then our well type, we are going to have a producer, we have injector, we have water injector, like what we explained on water flooding. So we are going to just take it as our producer. Okay, we may also have an artificial lift. When I was talking about water flooding, I took time to just give a brief description of why we need the artificial lift method. We may have a situation where the reservoir is highly productive. That means they have done analysis and they have realized that the reservoir is at its maximum capacity, or at a good capacity, but there is no production taking place. So it may be that within the tubing or within the borehole, there is no energy enough to push the hydrocarbon to the surface. So what will now happen is they will now bring in an artificial lift method that will help to propel the hydrocarbon from the bottom of the wellbore right to the surface. So in that case now, we may have an artificial lift. I talk of the sucker rod pump, the electrical submersible pump, and the gas lift. Those are the three most common. So if you have any lift method, you have to select it here. But for now, we are just going to leave it as none. All right, we'll come now to our calculation type. We want to calculate. What do you want to calculate? Do you want to simulate only the pressure alone, or the pressure and temperature? In this case, we may have pressure only, we have pressure and temperature onshore and offshore. Okay, and then you may also have temperature and pressure. They talk of surface gradient. So you may now have to use but the geothermal gradient in order to determine the variation in temperature as you're moving down within the formation, not inside the tubing. We are not talking about inside the tubing now. We are talking about inside the formation, because you need to know the rate at which heat will be dissipated between our completion and the formation. So you might take just pressure only. If you take pressure only, you realize that this particular whatsoever we had in the middle here has disappeared. So if you have, let's say, pressure and temperature, you realize now that I've talked of the model. Which model do you want to use? But if you want to use only pressure only, you realize that this would generally disappear, because they are assuming that you know the temperature only. So if I take pressure only, let me say I take down, we'll give the software some time to do the manipulation. Okay, so you see what appears here. We will generally put the information that we have here. If you look keenly, you are going to see temperature survey. This is temperature survey. So if I double click, it means that you have to give now your temperature survey. That means there's a temperature data that you must have carried out. That's the reason why you don't want to calculate the temperature, because you already have a temperature data. But if I take this off, and so if I come back to this first one, if I now take pressure and temperature and I click done, you realize that it is now tick. You don't need to input, you don't need to do that again. So what the software will do is that they have to use all the information that you give to predict the temperature within the formation, the rate at which the temperature varies within the formation, So we are just going to, since we don't have the temperature data, we will leave it as pressure and temperature. It could be on land or offshore. So you have to decide that. Then what method do you want to use to predict that temperature? We have three types of methods. We have the rough approximation, we have the enthalpy balance, and then we have the improved approximation. Each one, anyone you decide to use will determine which information that you're going to have here, which information that we are going to have here. So we will not go deep into that because it's a little bit more complex. So we'll not go deep into that. We'll just use the rough approximation. We'll use the rough approximation. Then we come to our brine modeling. How do you want to model the salinity? Do you want to put it, do you have a value for it, or do you want the system to correlate and obtain the value of the salinity based on the input data? So we are just going to leave it as default because we are going to input the salinity. If not, you can use this correlation to calculate the salinity. Then we go now to well completion. We go now to well completion. For well completion, we have the well type. Under well type, we have cased and open well. So we'll go to our PowerPoint and take a little bit look at that. So we have, in this case, if you look at what we have here, this is our production zone. This is our production zone, and this production zone has no casing. So this is more or less open at this level, even though it has been cased right up to this point, but the production zone has not been cased. In this particular case, you don't need perforation because the production will just, the fluid will have that free space to easily move into the well ball. So you don't even need to perforate anything because the perforation is coming in to create space within the casing so that you can have that conduit for fluid to flow between the reservoir and the well ball. But since there is no casing here, you don't need perforation. We may have a situation where we have a liner. A liner is a material that it protects the rock a little bit, but it allows fluid to flow through it. It allows fluids to flow through it. So it is not just like a casing. It's not as hard as a casing. It's a little bit porous, so fluid can easily flow through it. That's why if you look at this diagram, you see these arrows showing fluid flow in different direction. Even here, you have fluid flow in different direction. But in a situation where the well has been cased right down to the bottom, this is now what we call a cased hole. This is an open. We consider this one as open, and then we consider this as cased. Once it is cased, you need now to perforate the casing before fluid can flow from the reservoir into the well ball. So these are our perforations that have been created. These are the perforations. You can either use explosive or perforation guns to create these perforations. Once these perforations have been created, the fluid now will easily flow from the reservoir into the well bore. So we are going to leave it as cased hole. Then we may also have our sand control. Is there any sand that is being produced alongside with hydrocarbon? That's another question that you have to answer. And if yes, you have to look for a means to control that sand production, because that sand production destroys the equipment a lot. So they don't want the hydrocarbon to be produced with sand. Generally, within our formation, we have larger sand grains. Then we have the matrix made up of minor, small particles of sand. Generally, during high production rate, what we will have is, if the production rate is higher enough, because they always have this cut-off value that we can always calculate. I think the software can do that based on the geomechanical properties. You can calculate the highest rate at which sand will be produced. Below that rate, there will be no sand production. Above that rate, you can have sand production. So if the drawdown is so high, some of the sand particles will be carried away by the hydrocarbon. So what they can do is to easily put some kind of equipment around that particular formation so that it filters some of the sand so that all of it does not get into the well bore, even though some will succeed to pass, but all of it cannot get, so it's going to shift a majority of it. So we can use what we call gravel packing. gravel packing are larger grains. They are larger than sand. They are larger than sand. You know that generally we have particles of different sizes. So gravel is a little bit larger than sand. So when we do this gravel packing closer to the formation, as the fluid is flowing, it's going to shift out some of the sand particles. And then we could also have what we call wire-wrapped screens. Wire-wrapped screens around it also, as it's passing through it, is going to shift out the sand particle, and then only the hydrocarbon now will be able to flow within the formation. So we are going to keep it very easy, very simple for now. So we are going to just have our sand control is none. We don't have any sand control. So these are all information that you can put in: the company, the field, the location, the well, the platform, and so on and so forth. And then for our reservoir, we have our inflow type. We may have multilateral well, or we may have a single batch. A multilateral well is a well that starts up with a single drill hole. Then within the well, you now have several minor well bores that have been drilled within it. That's what they talk. That's the meaning of multilateral. So you may have a single well at the beginning. So and then you now have some other wells that are deviated from that. So many targeting different reservoirs, and so on. So this is multilateral, but we are just going to deal with a single batch, because if you put a multilateral, you have to put the information for all the various reservoirs that are present within that particular zone. So we will just leave it as simple, and then we have our single batch. Okay, if we are through with that, all right, there's one aspect also which we have not talked about. We have, gas coning. So if I go to my PowerPoint, all right, I don't think there's anything here about gas coning. So let me just explain. We may have our reservoir. This is our well ball. We have our reservoir. We have the fluids that are segregated within the reservoir, like that. Remember, this is where our perforation has taken place, because what they are targeting just the zone where oil is. They are not interested in producing water. There's a lot of water on the earth, on the surface of the earth, so nobody's interested in water. So we have gas there. Even though the gas is useful, but it may be a distraction at some point in time because it's of low economic value. So what they are interested in most at times in oil reservoirs is the oil. So they have perforated this zone, and then you are now doing your drawdown. Fluids are now fluids are now struggling to move in that particular perforation because it's a region of low pressure. They are struggling to move into the region of low pressure. So you realize that around this perforation, not only the oil will be struggling to move, but the water underneath also will be struggling to move into that perforation. Will be struggling to move into that perforation. The gas also will be struggling to move also in that perforation. As a result of that, there's some kind of a bulging, a cone-shaped bulging of the water, of the oil water contact around this particular zone. And then we have another downward cone-shaped bulging of the gas oil contact around this particular zone. So this bulging is what we call water coning, and then this is what we call the gas coning. So for now, we'll just leave it easy. We will not include all this complicated stuff. So we are just going to assume that our well has no gas coning. And of course, if you realize that the water current is drastically increasing, what you have to do is to analyze the production data to know exactly the source of this water, because the source of this water must not only be from water coning, but it can also be from what we call channeling, or behind, or behind, flow behind casing, or flow behind casing as a result of a poor completion. The cementation job was not well done. So fluid water is moving from an underground reservoir somewhere else and is now migrating gradually into that cementing part, and then it now moves into the perforation. You may be feeling that it is water coning, meanwhile it's not water coning, meanwhile it is flow behind casing. So there are various methods that can be used to identify the source of water, and there's a particular plot which is called a Chan plot that can be used to analyze what is the source of water that is produced. So if we have done all of this, we will now take our done, and then all our informations have been inputted. So the next thing now is going to input the PVT data. Is going to input the PVT data. That's our next step. So what we have here is our solution gas oil ratio. Our solution gas oil ratio is the amount of gas that is dissolved in one stock tank barrel of oil. That's the meaning of solution gas oil ratio. If I have one stock tank barrel of oil at the surface and I'm forcing gas inside the stock tank barrel of oil, how many, or what is the quantity of gas that will fully dissolve inside that one stock tank barrel of oil? That's the meaning of solution gas, solution GOR. There are different types of GOR because solution gas is not the only gas within the reservoir. Remember, apart from the solution gas, we also have the gas cap. So there are different types of gas oil ratio when we are calculating this. But for now, all what we are interested in is our solution gas, because that's what is going to determine the shrinking ability of the oil. Because we know that as the pressure is dropping, this solution gas will be escaping. As the solution gas will be escaping, what is going to happen generally is that the oil is going to shrink. The oil is going to shrink. So let me see if I have any illustration here. All right. So I have, no, that's formation volume factor. All right. This my solution gas oil ratio. This is my solution gas oil ratio. So this is what we call our bubble point. The bubble point is the pressure above which no gas exists within the reservoir. All the gas has gone into solution. All the gas has gone into solution. So you realize that around this particular point, above the bubble point, there is no more, the gas cannot take any more gas again. It has taken the maximum amount of gas that it can take. So there is no gas that exists again. So there we are going to have a constant value. As you are now moving below the bubble point, as the pressure is dropping, more and more gas is being liberated from the oil. As a result of that, the solution gas is gradually reducing. That means the amount of gas inside the oil is gradually reducing until there will come a time where all the gas has been liberated, and then you now have your oil. You are now going to have your oil. So this is a very important factor to consider in hydrocarbon recovery. Then another important aspect also is what we call the formation volume factor. What is the formation volume factor? It is the volume of oil at any reservoir condition divided by the volume at the standard condition. So if I have the volume at PT condition divided by the volume at the standard condition. Remember, the standard condition is the highest, is the lowest volume, not the highest. Instead, is the lowest volume that it can have, because at standard condition, all the oil must have been liberated. So at any given point in time, I expect this value to be greater than 1. Either it is greater than 1 or equal to 1 if the volume at any PT condition is the same as the volume at standard condition. Because at PT condition, the the oil occupies a larger volume because of the gas in it. All right. So what will happen now is, remember, if this is our PT, if this is our bubble point, above the bubble point, no gas exists within the reservoir. So now, if we are starting at a reservoir pressure that is higher than the bubble point pressure, as you are decreasing the pressure, what is happening is the formation volume factor is increasing. The question now is always, why is it increasing? Because if it has gas, I expect that as gas is being liberated, the volume should instead shrink. Then the formation volume factor should instead drop. But as you are dropping it, what is happening is the formation volume factor is instead increasing. This will come back to the concept of bubble point pressure. Above the bubble point, no gas is existing. So this increase in formation volume factor is not due to any effect of gas. This is due to what we call compressibility. So what you are doing when pressure is dropping is that you are reducing the pressure on top of the oil. And generally, when pressure on top of any material on the planet is reduced, that material tends to expand. So in this zone, the increase is simply due to the increase in volume due to the reduction in pressure that causes that expansion of gas. That is why you see the formation volume factor is increasing. When it reaches the bubble point, that gives us the maximum value of the formation volume factor. Below the bubble point, that is when gas starts being liberated. That's when gas is evolved now from the oil. When gas evolves from the oil starts shrinking. When the oil starts shrinking, the reservoir volume now is reducing. Remember, there is also expansion of what we have already explained here. Pressure is reducing, the oil is expanding, but the effect of gas outweighs the effect of that expansion due to reduction in pressure. So as pressure is reducing, it is expanding, yes, because of reduction in pressure. It is also doing what? Reducing. Why? Because of gas is being liberated. So there are two things taking place at the same time: expansion and shrinking. The problem now is which one outweighs which. So the effect of gas liberation outweighs any other effect. That's why the formation volume factor is reducing, meaning that the volume of the oil at reservoir condition is now gradually reducing because of the reduction in pressure. So these are basic properties that we have to look at. I said these are the key concepts in petroleum engineering as a whole. That's why I decided that let's take it gradually. That's why I decided that we should take it gradually. So we might not even reach where we ended yesterday, but no issue. We will still finish the prosper within the week. Even if it means using Friday and Saturday, we will still finish the prosper within the week. So I'll go back to my software. I have my solution gas. I think I have a data here for that. My solution gas is 449. Oil gravity is 29.9. So my solution gas there, 449. Oil gravity is 29.9. And then we could also look at the gas gravity. Gas gravity is 0.857. 0.857. And then our salinity is 200,000. Salinity measures the amount of chloride ion, or simply potassium chloride within the oil. So they may generally give you this as water salinity in parts per million. You can always toggle these units. I think there should be a way to change this unit if possible. All right, maybe this version does not change unit. I'll recheck again later. All right, so generally, if what has been given is the amount of chloride percentage with the amount of chloride within that particular fluid, what you would do is to multiply it with 1.6 to get the salinity in parts per million, because salinity can be given in chloride percentage or in parts per million. But if you are using it in parts per million and what has been given is a salinity in chloride percentage, you multiply it by 1.6 to get the value in parts per million. We may also have some contaminants in them, like hydrogen sulfide, carbon dioxide, and nitrogen. But for now, we are just going to leave it easy as 000. All right. There are some other properties. Remember that generally PVT analysis is done in the lab where fluids is collected. They take it to the lab, they analyze it to get the bubble point, the oil formation volume factor, to get the solution gas oil ratio, and all of that. But generally, the measurement that is done in the lab cannot cover the wide range of pressure possibilities that we have. Because remember, we are dealing with pressure from reservoir pressure, which may be very high, like 6,000, to surface pressure, which may be very low, as 100 psi. So if you want to use only the laboratory data, then you have to carry out analysis for all of these pressure ranges that we have. But generally, that is practically impossible for it to do. So what we will do now is, instead of using the data, the laboratory data, what we will do now is to use correlations instead to calculate this PVT parameters rather than using the laboratory data. So you have different correlations that can be used. We have Glassio, we have Standing, we have Lacaster, we have Vaques and Bex, and all of that. All of these correlations you can always get. I don't know if I have some of the formulas here, but in any petroleum engineering book, you can always get, I'm not sure I have any of the formulas for the correlations here, but you can always get each of these formulas. That means Glassio has a formula to predict bubble point pressure, to predict oil formation volume factor, and to predict RS, that's solution GOR. So Glassio has this formula, same as all of these guys that we have here. So if you're writing a project and you want to use probably the Glassio correlation, now you have to look for all of the formulas that he has used in order to predict these particular parameters. Then for oil viscosity correlation, we have the Bill et al. You can also toggle it down. We have Bex et al. And so many others that they have also worked on such things and have brought out standard equations that can be used to predict these particular properties at different pressure conditions. The problem now is some of these correlations can best work in some particular conditions. For example, they may tell you that Glassio is more effective for gas oil ratio between 100 standard cubic feet per stock tank barrel. That's what that correlation, that's where that correlation is most appropriate. So you have to check all those conditions at the beginning so that you know exactly which correlation you have to use. But the problem now is we have to always do a matching to see which correlation is the best for this particular data that we have, because they may have carried out some, but within range of PT, but within a particular range of PT. What we're going to do now is to match this data to the various correlations so that we will now know exactly which correlation is the best appropriate correlation. If you look at all of these correlations here, you realize that we have for oil formation volume factor and RS, we have glacial. These are the parameters here. We have parameter 1 and parameter 2. We have the standard deviation. We have the standing and correlation is the one with parameter 1 that is closer to 1, parameter 2 that is closer to 0, and then the lowest standard deviation. So I'm going to do a matching, a PVT matching, so that I'll be able to determine which of them is the best. I may have chosen glacial, but glacial definitely may not be the best. Go to match data. I have to input the pressure, the gas oil ratio, oil formation volume factor, and oil viscosity that have been measured in the lab. This is our PVT data that we have here. The first one is the pressure. I'll go to the software. I'll highlight this and I'll paste it there. That's our pressure. The next is the gas oil ratio. Copy. Gas oil ratio there. I paste. Then we have the oil formation volume factor. Remember, you see the values are greater than 1. As I explained, they have to always be greater than 1. I paste there. Then oil viscosity. I will copy. And then I will paste. I have to put my temp. Okay. So my temperature here is 280 and my bubble point is 2025. So my temperature is 280. And this is 225. All right, I'm going to click on match. Then I will take match all. Okay. So the matching parameter 2 and the standard deviation for all the methods have been. I will do now is I want to produce a plot to see which one is the best match. So I'll go to plot by temperature. All right, I have this. This is the temperature. This is for calculated data, and this is our field data. This is our laboratory data, and this is calculated. So we are seeing up here, calculated, and then match data. All right. So this is the one that the software has calculated. I will take, for example, the gas oil ratio. I double click on it. This is what the software has calculated based on the correlation of Bill et al. Based on the correlation of Bill et al. So I will go now to the match data. This is the match data. I will click now on the temperature and I take the same. I double click. You realize that it is now a good match. You now see that this particular correlation matches with the data. You can see different colors there. This one is for the match data. It's just that you might not see clearly because the two are almost coinciding. It must not be perfect for all. So I may come here. Let me see my oil formation volume factor. That's the oil formation volume factor for match. I go to the temperature up. I take it also. All right, you see that this one may not be that kind of a perfect match, but it is still not bad. It's still not bad at all. All right, so I will close this up. And then I'll go to parameters. I'll click on the parameters that we have. We have, for bubble point, I have glacial. You look at the parameter 1. We said parameter 1 should be very close to 1, and parameter 2 should be closer to 0. Then our standard deviation should be the smallest. This one has no standard deviation. So for bubble point, I will look at it and see which one is the best. This one is closer. Some of them, you may not see a big difference between any of them. But remember that we are using one correlation for these three parameters. Use bubble point, I will use this correlation for bubble point and this one for solution GOR. No, you are using one for the three. So you have to choose the best correlation that defines the three of them well, not just one of it. So if I look at Glacio, I look at this, someone may be tempted to say standing is a better correlation for bubble point because this value is closer to 1 and then this is closer to 0 than this. Remember, negative 217 is closer to 0 than negative 250. If you have a number line like what is drawn in mathematics, you pass negative 217 before you go to negative 250. So this is closer to 0. So looking only at the bubble point, I may be tempted to say standing is the best. Whatever correlation I choose, I may change it here. Now I'll go now to solution GOR and I look at it. You will now see that for solution GOR, Glacio is the best correlation. This one, even though this one is closer to 1 than this, but if you look at parameter 2, this one is very far away from 0, but this value is very close to 0. And this one also has the lowest standard, even though it is not the lowest among all of it, but compared to this, it has the lowest. We will go now to Lacaster also. You see that this is closer, but look at this value, very far. Even though it has the lowest standard deviation, but this value parameter 2 is very far from 0. So we are choosing the best correlation that will define these three parameters well. If you look at oil formation volume factor, we have parameter 1, 2, 3, and 4. I will go back to this PowerPoint and look at it. If you see the oil formation volume factor, you realize that you have two regions that has distinct shapes. But if I come to the solution GOR, this one here is more or less constant. So it will not really change that much in this area, but it will change in this area. So parameter 1 and 2 is okay to define the correlation. But for this, we may use parameter 1 and 2 to define this region. Then you use parameter 2 and 3 to define this region. So we have two separate areas that is well defined, separated by our bubble point. That's the reason why for oil formation volume factor, you have 4 parameters. And then for oil viscosity also, you have to make a best choice for all of them. And I think build R could be the best. Even, BexAL, you can even use BexAL here. There's still no issue. You can still use BexAL there. They are very close to each other. They are very close to each other. So most of the time, if you see correlations that are very, very close to each other and you use, okay, for standard deviation, you realize that this one is the lowest. Standard deviation plays a very big role. So pay attention more on standard deviation. I have not said you should not pay attention on this. This one, definitely, there should be no big difference between them, but look at standard deviation well, because standard deviation is what tells you the difference between the value and the average value. Because remember, in mathematics, when you want to calculate standard deviation or variance, you have to be taking x minus the mean order squared. There's a formula that has x minus the mean order squared. So you are looking at how much it deviates from the mean. How much does it deviate from the mean? So standard deviation plays a very big role. So I'll prefer this correlation for my oil viscosity. So I will take done. I have done the matching, and I've plotted the graph to see if the parameters are actually match. Then I can now take done. Let me see. All right, you now see PVT is matched. You now see these parameters that we had just 1, 0, and all of that. The parameters have now changed. And then we have our correlations there. So that's how you do our PVT match in order to choose the best correlation for your data. I have explained already why we are doing correlation. The laboratory data is not sufficient enough to use for our calculations because it doesn't cover the entire range of pressure that we have. If I have, for example, if I go here, I'll look at the pressure is from 6,000 to maybe 600. What will happen now is if the pressure is 500 or 400, what would these properties be? So we will not be able to use this particular data to do our calculation, but we use that predict those correlations because the correlations will predict at any temperature and pressure condition is going to predict. All right. So I'll go back to the software. So we have inputted our preliminary conditions. We have inputted our PVT data. All right. So what we'll do now is we will come now to the third section. This is where we have to develop our IPR. I will go back a little bit to the PowerPoint of nodal analysis that I explained last week. I gave some equations that can be used. This is our visual equation that is used to develop our IPR. The IPR is used to characterize the performance of the reservoir. You can use the visual equation in order to determine this IPR because this IPR is the bottom hole flowing pressure against rate. So I can draw a graph of bottom hole flowing pressure against rate. So the only unknown in this equation is our reservoir pressure and our cure max. The easiest way for you to obtain cure max is to take the productivity index, this is the formula of obtaining productivity index, times the average reservoir pressure divided by 1.8. Once you obtain this cure max and put it there, you have the reservoir pressure, you can now draw this graph. I did this with Excel. If you have not visited it, it means that you are not ready for the internship. All right. I said generally, what will happen is they don't use the productivity index in real field cases because this productivity index comes with so much uncertainty. The formation volume factor, there may be an error in determining it. The viscosity, there may be an error. The skin also, there may be an error. So this particular J value may come with so much uncertainty. So what will happen now is, in order to construct the IPR, they have to do what we call testing. They have to use a test point. That means they just have a particular flow rate. They just measure a particular flow rate and the bottom hole flowing pressure. Just that one value alone is enough to generate the IPR. If this particular test point that we have, which is made up of a flow rate and a bottom hole flowing pressure, if this particular test point is above our bubble point, because this is our bubble point pressure, you are going to use this formula. You use this formula to calculate G. You use this formula to calculate the flow rate at the bubble point. Then you use this formula to generate your IPR. If the test point is below our bubble point, you use this formula to calculate J. You use this formula to calculate J. Remember, in calculating J, you are using your PWF and your PR. No, your PWF and your cure zero are the values at the test point. So I will use all of this now to calculate the value of J. From there, I'll calculate the flow rate at the bubble point. Then I will use this equation now to generate our IPR. So in order for you to use the visual equation to generate the IPR, you must know the test point value. So I'll go now to our software. You can generate it by using the IP. This IP works only when the reservoir pressure is above the bubble point. It generally gives you just a straight line. So I will use visual equation. My reservoir pressure, I will say, let's say 4,000. Then my temperature, our reservoir pressure was 280. our water curd, we'll just leave it at 0 for now. Let's just assume that the well is not producing water for now. You realize that for this Vogel equation, you must have this test rate and the test bottom hole pressure. So I'm going to put the value here at 250. Let's just assume that our rate is 250, and then the bottom hole flowing pressure, that those test values is 2,500. Okay. From there now, I will go now to, once every information has been entered, you realize that this reservoir model, which was initially showing red, is now green to show that the system is ready for calculation. So I will go now to calculate. Then I will, all right, the calculation has been done already. Once the calculation has been done, I can now plot result. I will plot my result. On the x-axis, I have my flow rate. On the y-axis, I have my pressure and temperature. Remember, at the beginning, we inputted that we want the software to be able to predict our temperature. That's the reason why you are now seeing this temperature here. So we have, okay, so this is our IPR that has been generated. If we're able to draw this using Excel, if you follow our classes of last week, then you should not be surprised with whatever we have had here. That's a temperature. So we could always plot. Let me plot again. I could always take out the temperature. Then I see just my IPR. I see just my IPR. Then I want to look at the result also. View results. So these are the results. So this is how the rate is changing with pressure and temperature. There is no temperature change, no temperature drop due to skin effect. We have not come to this. When we go to the skin effect due to deviation and perforations and all of that, we'll see how all of these skin values could be calculated. But for now, we are not having anything about that. So we have done. So our IPR has been created for using the Vogel equation. Using our Vogel equation. You could always use the PR if at all it is above our bubble point. The reservoir pressure is above our bubble point. But remember, our productivity index here is equal to what? PI. But if you choose this particular method, you still end up having a curve, not a straight line. Let's see. Let's assume that we have our productivity index is 0.2 stock time barrel per day per PSI. Let's assume that that's our productivity index. We calculate, we just the pressure. You see that the answer does not look it is IPR not is. You remember that in our P analysis, we bubble point pressure. So immediately the software is predicting, even though it's using the IPR, immediately the pressure drops below the bubble point, the system is already that IPR model cannot go. You cannot have the linear model again. That's why you are now seeing the curvature that is happening there. But in this case, we will have just our productivity index. We'll have just our J value that we had there in the calculation. This is what we call productivity index, this J. So from here, you can see everything. All right, we have already seen result. This is AOF, which is 220. AOF is absolute open flow. This is a maximum flow rate at zero bottom hole flowing pressure. That means it is our maximum rate. Oh, I didn't choose any plot. Oh, okay, rate. All right, so this is a value, absolute open hole flow, the maximum flow rate at zero bottom hole flowing pressure. That is not a realistic, it has not been realistic because there's no way it can actually reach that level. This absolute open hole flow is actually the cure max that they have used in this equation. is actually the cure marks that have been used in this equation. This is actually the cure marks that have been used in this particular Vogel equation. All right, so we'll take this done. We'll go back to our Vogel equation. So when you are using the Vogel, there is no way we can talk of skin because Vogel equation does not take into account any skin effects. But if you want to start bringing in the skin, remember, it is already very simple at this stage of sand control because we took none. If I now take gravel packing, if I click on gravel packing, you now realize that the tab for sand control has appeared. It means that I have to put the information for sand control here. But when I take none, it disappears. So at this level, we have been able to define our system, input our PVT, and we have done the PVT match. Then we have constructed the IPR using simple equations like the PI and the Vogel equation. So I think we should end there for today. We have gone more than 1 hour. So I think we should end there for today so that you can digest this part first before we continue from there tomorrow, 3:30, please. So I will